All right, 18F. 18F is called applications of motion, but essentially it's kind of like kinematics. Now, if you do physics, some of these terms will seem a bit more familiar to you. If you don't, I've already put the definitions in this table for you to read, but in a nutshell, this is what it is. Position, velocity is different to speed and distance. See, a position talks about relative to a particular point. Distance doesn't matter about relative to a particular point. It just matters how much you cover. An example, just so that you can sort of visualize this. If I'm standing right here, let's say at point 0 on a number line, that's position 0, right? But if I go 2 steps to the right, so I go 2 steps to the right, and then I go 2 steps back, it almost feels like I've gone nowhere because the position is still the same. So where I started and where I finished, still the same. So position talks about relative to a certain point. So it's relative to this particular point. But have I moved? Yes, I have. I've technically have burnt some calories. I've walked 4 steps. But in the position, it looks as if I haven't gone anywhere. Okay, so that's one of the key differences between them. Position will just be more about relative to a certain point. Doesn't matter how many Ks you ran. Even if I ran 20 Ks this way and ran 20 Ks back, on the position, it looks like I haven't moved, right? But I clearly have. So that's the difference between distance and position. Velocity is different to speed because there's a direction. When you talk about speed, you say 60 kilometers per hour. You don't talk about whether it's 60 kilometers per hour reducing, like you're trying to stop the car if you're driving. Are you reducing the speed at 60 kilometers per hour in that particular speed, or are you increasing the speed to 60 kilometers per hour? So velocity has a direction. Okay, so those are just some definitions. You can read through my definitions there to help you understand the key concepts. But what do you take out of this exercise? How does it relate to calculus? This page. This one. This is all you need to know. So I talked about position and velocity so far. We say if you have a function where we use x to represent position, so where are you on the number line? If it's x in terms of time, so position is relative to time, okay? Then the derivative, so delta x, delta t, so the rate of change of your position as your position changes over time, that's what it's saying. So if I drew an axis and x represents your position, t represents your time, then whatever graph you get, the derivative of that will tell you the velocity. It's very similar to had we done it this way. Back in year 9, you did distance versus time. And when you learned linear, distance over time is your speed. It's like 60 kilometers per hour. If you never noticed, 60 kms per hour, that actually is distance divided by time. That's why we say speed is distance divided by time. So when you draw this graph here, what you're actually saying is every y value over x value, so y over x is rise over run. So y divided by x will give you the gradient. That's why the gradient, which is the derivative. Okay, so here was position, velocity. This is distance, time. So they can give you a distance formula in terms of time, and then the derivative of that will come to speed. This one is position graph. Derivative of position graph gives you the velocity. And then the double derivative, meaning if you derive it again, so if you derive it again, so the derivative of your velocity function will give you your acceleration. Again, if you want to know the difference between velocity and acceleration, I already wrote a description. But in a nutshell, there is a difference between velocity and acceleration. How so? Acceleration, think of it as how fast did it take you to get to a certain speed. So for example, a Formula 1 car, why is that so special? Because it can reach 100 kilometers per hour in a few seconds. But if you got my Honda CR-V and you said, how long does it take to reach 100 kilometers per hour? It will take much longer than a few seconds. So what's the difference between the two? It's the acceleration. It's how fast it reaches a certain speed. You see that? So how fast it reaches a certain speed. And speed is what we talk about rate of change. That's the derivative. So it's like saying dv dt is my speed or velocity because it's got a direction. And how fast it gets there, that's called the acceleration. Does that make sense? Okay, so you just think about Formula One car versus your normal car. How fast does it take? Or how long does it take to get to a certain speed? That's what acceleration is. So today's exercise, we're going to do two problems where we relate position to velocity, velocity to acceleration using calculus so that we can answer the questions in a nutshell. Cool? All right. Flip over the page. Let's do an example together. So we've got some terminology. You've got to flip back and forth just so you can read the definitions. But that was the key takeaway points. Okay, position, derivative position gives you velocity, derivative velocity gives you acceleration. Okay. All right, let's flip over the page. Here we go. Oh, before we do, if you're looking at this notation, you're a bit intimidated by what I wrote here. This just means d is delta, means change. So when we say dy dx, it just means change in y as change in x, meaning as y increases, how does that affect as x increases? Yeah? So notice, why do I have double d's? Because I derived it twice. I did derivative of x by derivative of t, and then I did it again. I said derive whatever this is by time again. So we normally write it like this. We say d2x over dt squared to represent double derivative. Okay, sometimes we might even do 1 dash for derivative once, and then we do f double dash, that means double derivative. Okay, just some notations in case you see that in your textbook and you're wondering what it means. Okay? All right, let's do this problem. Here we go. Example 16 in your textbook, we've got a particle. A particle moves in a straight line so that its position, so that's keyword there. So when you see the word position, you should start to think about 18F. If you see that on a sack or you see it in a problem solving, yeah? Bring out your CAS, and then you should start from there. So here, we said x centimeters, so that's representing the position relative to O, which is the origin. This represents origin. So starting point. At time t seconds is given by, so they give you a formula. Here's your position graph or position equation where t is greater than or equal to 0. First question was, find its initial velocity. When you see the word initial, what should you be thinking of? It's always a hint. They usually do that. What's initial hint out to you? What are they trying to imply? What information can you take when someone says initially? Or initial. Yes, Muffy. At the start. Now, at the start, what information can I say about this equation? What can we say? What equals 0? T. Not x. Because we don't know where the position is. I don't know where I'm starting. But you do know before you start the timer, isn't the timer at 0? Because before you start the time, before the particle ever moves, initially must be at the very beginning. If it's at the very beginning of time, that's 0. So that was hinting when you see the word initial or at the start of something or the beginning of something, the hint is t is equal to 0. That's what they're saying, not position, because I don't know where I'm starting. I could have started 10 kilometers after the start line. Who knows where I'm starting at? But what I need to know is initial is t equals 0. All right, next one. So I know t equals 0, but what am I trying to find? I'm trying to find velocity. Now look at the notes I've given you. I don't have a velocity equation. How can I get a velocity equation? Based on the notes I've given to you. It's one hint. What do you do? Mete.
So it's the change of position over time. So it's the gradient.
Yes, that was very complicated wording, which is correct, but we're simply saying find the derivative of this graph. Yeah. So remember, this is your position graph. X equals to t squared minus 7t plus 6. And already in my notes here I said, if you want to get your velocity, it is the derivative of your position equation. Yeah, delta x, delta t, x represents the position. So here we go. If you want to find velocity and you want it to know when t equals 0, well, I need a velocity equation to begin with. So to find velocity, derivative. So delta x, delta t is the velocity. And let's go. Power rule again. Power rule is like your bread and butter here. Artie, what is the derivative of t squared minus 7t plus 6? 2t minus 7. Beautiful. So I went from a quadratic to a linear equation. That was my position graph. So I'm going to write here position to remind you. This is position. Tells you where you are on the x-axis. This tells you how fast I am at that particular point. So here we go. What do I want? I want to know the velocity initially. And initially means t equals 0. So here, this is my velocity equation. V is equal to 2 times t minus 7. What's t? T 0. So initially, that's the starting point. When t is 0, my velocity is at -7. Now, did this say meters or what does it say? Centimeters and seconds. So that means it's -7 centimeters per second. So at this particular starting point, somehow at that particular point, maybe I was running and then someone started a timer and I just slowed down at -7 centimeters per second. So this particle, when the timer had started, they were already reducing or they're left. We don't know what that -7, that position per second means. That minus, we're not sure yet. Okay? But we just know it's -7 centimeters per second. All right, that was part A. So far, straightforward? Yeah, just using the key takeaway table. Part B, let's do this. B, so now I've got velocity, the initial velocity. When does its velocity equal 0? So they're asking for time now. They're saying when, so find the time, find t, when v is equal to 0, and then, says and, what is its position at this time? So it's asking for x as well. So find time and then find x. So here we go. We want to know when v equals 0, velocity equals to 0. When does that happen? We've got a velocity equation. Velocity equation is 2t minus 7. So you're really asking this. You're just saying if v is equal to 2t minus 7 and v is equal to 0, what's t? Solving for this, let's go with Lucky. 0 equals 2t minus 7, so t must equal to? 702. Add 7 on both sides, you get 2t. Divide both sides by 2. 7 on 2, which really means 3.5. This represents, therefore, t will equal to 0 at 3.5 seconds. So this particle, when will this particle get a velocity of 0? And velocity of 0, doesn't that just mean speed 0? If speed is 0, doesn't mean it's when it stops. Get me? So you got to think about the application here. When is the particle going to stop? Well, the particle will stop at 3.5 seconds. Okay, so the position will get to 0, the velocity is 0, when it reaches 3.5 seconds. But then they ask, where's the position? So where's the position at this time? So where is x if I know t is equal to 3.5? What do you do now? How do you find the position? What do? You figured out when, Mumafi. Yeah, because the original equation tells you the position. That's your position equation. So your position equation was t squared minus 7t plus 6. So here we go again. X is equal to t squared minus 7t plus 6. And you're just saying when t equals 3.5, find x. So here we go. This is where if you used a calculator at this point, we can just type it in. I'm going to cheat and just put it in a calculator right now. Let's see what we get. So So we go t squared minus 7t plus 6. So define x of t is equal to, what is it, t squared minus 7 times t plus 6, and then x of 3.5. Negative 25 on 4 or negative 6.25? Or negative 6.25. Now this is centimeters, this is the position. So what does this mean? What does it mean when you say position is negative 6.25? Remember, you've got a number line. It started off at an origin, which is the center point. Positive usually means towards the right, negative means to the left of where the starting point is. So we know that after 3.5 seconds, it will now end up at negative 6.25. This is where the particle is after 3.5 seconds. So draw out the diagram, because one of the problems here is that you have to learn to read what happens to the particle. Because sometimes it goes left, stops, then it goes back to the right after a certain time, which is one of the exercises that you're going to practice doing, and drawing it, representing the scenario will help you understand. And where was your position? Remember, the position was at, initially you were starting at velocity as negative 7 centimeters per second. Okay, well that doesn't help. Where do we start? We start at positive 6. Notice here, if I had to look at this graph at t equals 0, the position is at 6. So that means you would have started here. See that? So I'm just looking at the equation. Initially, t equals 0, you started at 6. After 3.5 seconds, you ended up left of where you are. Okay, so relative to the origin, I was starting at 6 centimeters from the origin, and then after 3.5 seconds, my velocity stopped, or particle stopped, and I'm now 6.25 centimeters from the left of the origin, position-wise. Okay? Is there a follow-up question after that? Let's see. What else do we also have? Determine its average speed for the first 4 seconds. Oh no, so C. What is its average velocity for the first 4 seconds? So average velocity versus all right, key difference between the two. Velocity and average speed. If you flip back to the first page, I already put a note here for you. Average velocity is change in position over change in time. So it means we're x1 to x2, right? How far is the positioning? Versus distance. Remember, positioning is different to distance. So for example, if I said, what's my average change in position? If I started here and I took 1, 2 steps to the right, and then 2 steps back, my position hasn't changed. So the average change would be 0. But for my speed, distance-wise, I have made a distance. I did 1, 2, and then 3, 4. So I have moved. So therefore, distance would be 4 over how long it took me to do that distance. Okay, so be careful between velocity and speed. One is about position, one is about distance. So let's look at our diagram again. Let's answer the question and look at the diagram. They said the first 4 seconds. There's a couple of details here that if you don't draw the diagram, you may not have seen. See, initially was when t equals 0. I then sub-t to the position graph, and I got x equals 6. Okay, so position graph was this one. Here's your position, t equals 0, then x will equal 6. So what does that mean? At the very start, your particle was 6 centimeters away from the origin on the right side. Okay, so here's the starting point. I'm just going to put a number 1 to remind you. So you started here. You started at 6 centimeters away. After 3.5 seconds, you ended up at this point now. X equals to negative 6.25. So you moved after 3.5 seconds to this point. But they were asking for the first 4 seconds. This is not 4 seconds yet. I still have another 30 seconds that I haven't accounted for. So now you need to find where is the position at 4 seconds. Does that make sense? Okay, so we've got the start, we've got 3.5, but we don't have, where's the final point, which is 4 seconds. So here on your page, let's work out where is the position, because t equals 0, we knew the position was 6 centimeters. But what about t equals 4? Where's my position? Okay, so let's work that one out. Your position equation was t squared minus 7t plus 6. If it was 4, it should be 4 squared minus 7 times 4 plus 6. Let's work out our position. I'm going to type it in my calculator. So x of 4 gives me negative 6. Now I want you to look at the diagram. Hopefully you've drawn the diagram in your own problem. Have you noticed something? See, there's a difference between distance and position now. I'll draw it again, just so you can visualize what's happening. So here's the origin. You started 6 centimeters away on the right-hand side of the origin at t equals 0 initially. 3.5 seconds later, you ended up at negative 6.25 centimeters left of the origin. This is at t equals 3.5 seconds. So you've gone this way. So this is where the particle is. The particle has moved to the left. And then when did you finish? You finish at 4 seconds at negative 6. Where's negative 6? Is it towards the right or towards the left of this point? Because that was the last thing that we knew. Where's negative 6? Is it over to the closer to the origin or away from the origin? Closer to the origin. 6 seconds is over here. Yeah, so negative 6 now brings us here now. So what does that mean for the particle? That means the particle had a velocity of 0, it stopped, and then it must have returned or did a U-turn, and it went back to this point now, and that is when t equals 4 seconds. So if I asked you what is the position from the starting position to the ending position, can you see my starting position was 6 centimeters, which is this one. I started here. X equals 6. Let's call it x1. x2, my final position, I ended up here now. x2 is now at negative 6. But the reality is I've actually moved more than 12 spaces or units away. I didn't just go from 6 to negative 6. I actually went from 6 all the way to negative 6.25. So that's a distance of now 12.25. And then an extra 0.5. 0.25. So overall, how far have I traveled? I've traveled from 6 to 6.25 is 12.25 plus another 0.25. That makes it now 12.5. Okay, so I've moved 12.5 distance. Position-wise, though, I went from 6 to negative 6. See the language I'm saying? So distance is different to how many steps I've taken versus where am I in terms of position. So when we say average velocity is the total position. What is the total position? So position was x2 minus x1. So I went from negative 6. So final position is negative 6 minus my initial position. So negative 6 minus 6. And then what's my final time? My final time was 4 seconds. Take away my initial time. 0 seconds. Okay, so this is position, not distance. What does that give me? That gives me now negative 12 divided by 4, negative 3 centimeters per second. This is my average velocity because I'm taking the total position, not total distance. Versus if you were to do now average speed. See, average speed is different because this now wants to know what's your distance, your final distance, minus your initial distance over the time. Now, the time's still the same. It's 4 minus 0. But the difference is the distance. See, distance I start off at this point, which is 0. My distance I started at 0. I haven't moved. Then I moved all the way here. That's negative 6.25. Then I went an extra 0.25 back. So if you add that distance there from 6 to negative 6.25, that's a total distance of 12.25. And then you turn back another 0.25. That's now total 12.5 distance. Okay, so you started off at 0. I'll just write it again. And you've traveled a total of 12.5 distance over 4. So 12.5 divided by 4 gives you 3.125. Do you see the difference? One is about distance, one is about position. And the best way I can describe it is think about how I was moving. So if I took 2 steps to the right, 2 steps left, position-wise, I haven't moved. My average position is 0. But in terms of distance, I have moved. I went 4 steps to the right, 4 steps left. You can't say I haven't moved. That's why it's funny if I did a 20K run to one direction and then it came 20K back, you can't say just because I ended up at the same spot, I haven't moved. I clearly have. Okay, so one is about how far you travel, and one is where are you on the map? Have you moved away from the map? Okay, so when you're working for average velocity, you're looking for total positioning. Starting position to final position. When you're looking for speed, you're looking at your starting distance to your final distance. Okay, that's the main difference between the two. Cool? All right, I'm going to stop the video there because that is pretty much that little hidden movement that's happening with a particle. That is 18F. If you got that, you don't have to do many more problems. Just do one more, get the sense of it, and then move on. Because that's the only part you really need of 18F, which is this one, the takeaway page. So the takeaway of position, velocity, acceleration is really all we wanted you to take out of it. Okay, obviously the problems are getting a bit more funky with different equations, but the idea is the same. Okay, let's stop the video there, and I'm going to